Okay, good morning. Today we're going to discuss complex eigenvalues for systems of equations. And so let's start with an example. So if x prime is equal to minus 1/2 minus 1, 1 minus 1/2 times the matrix x, um, then this is a matrix with all real entries, but as we're going to see in a minute, we get complex eigenvalues. Okay, so let's start to find, and we just want to find the general solution. So here's how we start. We let, as always, we start by finding the eigenvalues of A, where this is the matrix A for this problem, obviously. Okay, so we find the eigenvalues of A. So that means I have to look at the equation, the determinant of A minus lambda I equals 0, excuse me, and solve that. So that 0 is the determinant of the matrix minus 1/2 minus lambda 1 minus 1 minus 1/2 minus lambda. And so that's a 2 by 2, so that's really easy. So we get minus 1/2 minus lambda quantity squared plus 1. So that says 0 is, this is lambda plus a half quantity squared because the minus sign when it gets squared goes away. So this will be lambda squared twice the product of the two. So that'll be plus lambda. And then the plus the square of the second will be a fourth. Okay. And then we have to add 1. Okay, so let's see. That is um, so um, actually, the better way to do this is not to write this out this way. Let's not write this out. Notice that if I factor out the minus 1 and square it, then I can get this as lambda plus 1/2 quantity squared plus 1. So you think of this as an equation like alpha squared plus 1 equals 0. So that says alpha is equal to the square root of minus 1 plus or minus that. Okay, whoops, sorry, a little bit off the paper. And let me try to get this to focus a little better. There we go. Okay. All right. And so but this is, here's my alpha. So this says lambda plus 1 squared is equal to minus 1. So if I take square roots on both sides, it says lambda plus a half is equal to plus or minus the square root of minus 1, which is I. So that says that lambda is minus 1/2 plus or minus I. Okay, so there's my two eigenvalues. So let me call them lambda plus and minus. Okay, notice those are complex eigenvalues, even though the matrix we started with was real. So that just happens sometimes. But we still follow the same procedure. Now we have to find the eigenvectors. Okay, so let me take lambda plus, which I called that's what I mean by minus 1/2 plus I. Okay, and so now what we have to do is we have to look at A minus lambda plus times the identity times, let's call it x plus for that eigenvector corresponding to lambda plus equals 0. Okay, and we'll say the components of x plus are x and y. And that's what we want to find, the x and the y. Okay, so what is A minus this? Now be real careful. Here's your matrix where you wrote A minus lambda. So now our lambda is minus a half plus I. So this becomes the matrix minus a half minus a half, so minus a half, so the 1/2s go away, and then you have to subtract I. So I get a minus I, and then in the next term it's 1, and then down here it's minus 1, and here again you have the same thing. You have minus 1/2 minus a minus 1/2, so those cancel each other out, minus I, okay, times xy equals 0, 0. Okay, so that says minus x plus, sorry, minus ix plus y, whoops, equals 0. And the second equation would better be the same as the first. Now, when they're complex eigenvalues, it's not obvious like they are when it's real eigenvalues, because it's a little harder to see that one is a multiple of the other. Not very hard, but a little bit. But now you can see that actually these are the same equations, because if you multiply the second equation by I, if you were to take this one and multiply by I, what would you get? You would get minus ix, and then you would have I times minus I. So that would be minus I squared, but I squared is minus 1. So this would be plus y equals 0. And that's the same as the first equation. So you see they are the same equation. It just doesn't look quite as obvious as it did in the other case. So here's the equation we're going to work with. So that says y is I times x. So x plus or an eigenvector that goes with lambda plus could be pick x to be 1, and then according to this rule, y will be I times 1, okay? And any constant multiple of this is also an eigenvector, okay? That's fine. So now we found that one. Now we need to find the eigenvector corresponding to lambda minus, okay? So for lambda minus, that's minus 1/2 minus I, and we need to solve a minus lambda minus I times, let's call it x minus, equals 0. And I don't know, you could call it x and y again, because we already found what those are. You can call it u and v if you don't like using the same letters for two different things in the same problem. Fair enough, okay? And now let's go back where we can see the a minus lambda I. If you look right here, you can see this right here is the matrix A minus lambda times the identity. So now we want to use lambda to be lambda minus. So A minus lambda minus I will give me the 1/2s will cancel again. And then you will have, you're subtracting a minus I, so that gives you a plus I. And then you get 1, and here you get minus 1. And then you'll get 1/2, the same thing that you got before. So you'll get an I times UV has to be equal to 0, 0. So that gives you two equations, and it says I times U plus V equals 0. And it also says minus U plus IV equals 0. And those better be the same equation, or you've made a mistake so far. So let's see. Is it, if I multiply this equation by minus I, that's a minus there, minus I, then I'll get minus I times minus U will give me IU. And then here I'll get a minus I times an I. That'll give me a minus I squared, so that will give me a plus B equals 0. And that's the same equation as this one. So these are the same. Okay, you need that, or else you've done something wrong at this point. Just, okay, so from this one, this says that V is going to be minus I times U. So an eigenvector for lambda minus could be, choose U equals 1, and then V is minus I. Okay. All right, so now when we write down the general solution, Okay, so the general solution is going to be C1 times the first eigenvalue, which was minus 1/2 plus I times t, times the eigenvector lambda plus, which was 1, which was 1I, plus C2 times e to the minus 1/2 minus I times t, times the second eigenvector, or the eigenvector that went with that, the one we found second, which is this. Okay. All right. So notice that could be written as there's a e to the minus t over 2 in both of these guys. So this is e to the minus t over 2 times. The first one is C1 e to the it, which is cosine t plus I sine t, times the eigenvector, this. Okay, I just factored out the e to the minus t over 2. And if I factor out the e to the minus, oops, that made a smear, sorry. If I factor out the e to the minus t over 2 from the second one, I'll get C2. Now I have e to the minus it, which is cosine t minus I sine t, times the second eigenvector. Okay. Okay, so rewriting that last line we had on the previous sheet and factoring out the e to the minus 2t, so that's times all of this. If you rewrite things carefully, you see you get C1 plus C2 times cosine t, and then minus C1 plus C2 times sine t. And then if you look at the terms that have an I in them, it is C1 minus C2 times sine t in the first component, and then I times C1 minus C2 in cosine t times cosine t. And so notice that you have the same constant. If you like, you could call C1 plus C2 C1 hat, and then call C2 hat C1 minus C2. So you have C1 hat cosine t minus C1 hat sine t. Okay, and then here you have I C2 hat sine t, I C2 hat cosine t. And so looking at that and rewriting it, factoring out that C1 plus C2 term, and then I'm going to write the exponentials back with the sines and cosines. We have a e to the minus t over 2 cosine t, e to the minus t over 2 minus sine t, the I, and then I factor out the C1 minus C2, and then I have the exponential times the sine and the exponential times the cosine. So think of this as two functions, a constant, that's my C1 hat, times u of t, plus I times another constant, that's my C2 hat, times v of t. Well, in the last video, or the previous video, you saw that if you have a solution that's of the form u plus iv for u and v real matrix functions, if that u plus iv satisfies the matrix equation x prime equal ax, then u and v individually also satisfy the same matrix equation. So that means that because we've written our solution, x of t, as a linear combination of u plus iv as a solution of the matrix equation x prime equal ax, then u and v individually solve that equation, okay? And so the fact that each one of those individually solve that equation means we have our answer in terms of real valued functions, okay? So that's how you can get the complex eigenvalue case down to real valued functions. It's not a short problem, and it takes a while to do it, but with some practice, it's not that hard. It's sort of the same routine over and over. Okay, so now practice the problems on the homework for complex eigenvalues, and then then you should head to the next lecture. Okay, see you again. Bye.